Group 3, gas absorption to equipment.
So, as the previous group discussed, gas absorption operation involves the separation of solutes from non-digestible gases mixtures by reduction to liquid solid. For the recovery, it is achieved by contracting the gas stream with a liquid that offers a specific solubility for the solute gas. Because in gas absorption, the material desired is in the gas phase, or the gas to be recovered. The application of gas absorption is for the purification process of gas streams, or recover valuable components of the stream. It is used extensively to remove toxic or noxious components or pollutants from the fluid gas stream. So, usually, the application of gas absorption is in environmental aspects. So, design procedures. These are the values or the things that should be remembered while designing equipment for gas absorption. The data on the gas liquid or vapor liquid equilibrium for the system at hand. Information on the liquid and gas handling capacity of the contacting device chosen for the particular separation problem. This would be the towers and the packets. Determination of the required height of contacting zone for the separation to be made as a function of properties of the liquid mixtures and mass transfer efficiency of the contacting device. Later on, we'll be discussing wet walled columns, and that would discuss this third sentence. So here are the values that we would be computing during the design process. The gas solvent, the gas velocity through the absorber, or the vessel diameter, the height of the vessel, and its internal members. The internal members would constitute the package in the tray. And the optimal solvent circulation through the absorber. The temperatures of the stream entering and leaving the absorber, the pressure, the mechanical design of the absorption and stripping vessel, including the packing and port. So here are the quantities that we will be discussing later on. The gas flow rate, the gas composition, the operating pressure, and the allowable pressure drop of the absorber, the minimum degree of recovery of one or more solutions, and possibly the solvency. So the third, fourth, and fifth quantities are economic considerations. So it's our So as we know, the solvent is one of perhaps the most important part of the gas absorption process. So in choosing your solvents, here are some of the considerations to make. The liquid with high solubility, or the solute which reduces the amount of solvent to be circulated. It should be relatively non-volatile, inexpensive, non-corrosive, stable, non-viscous, non-foaming, and preferably non-drinkable. So these properties are actually stated in incentives. So every solvent, usually all of these are the preferred solvent characteristics, even in the case. So definition of terms. some of these terms throughout our report. So the liquid to gas ratio, or the quantity of heat received to the absorber divided by the outlet gas flow rate. So liquid in over gas out. Fouling, foaming, and flooding. So fouling would also mean flooding. Then foaming is the formation of bubbles by the liquid. And then flooding is the condition when the liquid completely fills the void spaces in the packing and no more liquid flows down with the tower. So
for the design of gas absorption systems, you have two equipment. The first one is the tray or plate towers. It is often used in order to efficiently contact the vapor and liquid in absorption process. The liquid is maintained on the tray surface and prevented from flowing down through the holes by the kinetic energy of air or by using bubble caps in its holes. Overflowing liquid enters the downspout to the next tray below, and air is flowed through the holes or bubble caps and passes through the flowing liquid. So we have the gas inlet below, and the liquid is maintained in the trays, and then the gas flows upward and flows through the holes and to the liquid. So there you have contact between the two fluids. The next one is back towers. It is used for continuous counter-current conducting of gas and liquid in gas absorption. Consists of a cylindrical column containing a gas inlet and distributing space and liquid outlet at the bottom, gas outlet and liquid inlet at the top, and a packing or filling in tower. So gas enters the distributing space below the packing section and rises through the openings and contacts the liquid flowing downward the same opening. A large area of contact between the gas is provided by the packing and the liquid below the packing. So we have the gas inlet at the bottom and liquid inlet at the top. They flow undercurrently in the packing or the filling, and there you'll have the contact, a large area of contact between the two fluids. The two fluids continuously flow.
Tanungin mo na.
So, tanong lang. What is used for continuous countercurrent contacting of a gas and liquid in gas absorption? Next one.
To be considered before designing the gas absorption towers, three of which are the heat effects in gas absorption, another is the absorption of multi-component systems, and another is the gas absorption with chemical reaction. First is the heat effects in gas absorption. It usually accompanies an absorption process where a chemical reaction takes place. Liberation of heat accompanies an increase in the temperature of the liquid. So heat effects that may affect a gas absorption. So one is the heat of solution of the solute. It includes the heat of condensation, heat of mixing, heat of reaction. And it usually accompanies a rise in the liquid temperature. Next is the heat of vaporization or condensation of the solvent. Third is the exchange of sensible heat between gas and liquid. You know sensible heat, right? From thermodynamics. Yeah. And last is the loss of sensible heat from the liquids to cooling coils or the atmosphere via tower walls. Heat effect in plate tower. A heat balance must be done around each plate to determine resulting temperature. For adiabatic operations, the temperature of the stream leaving the system is higher than those of entering stream due to the heat of solution. So a lower solubility as the solubility of the gas is decreased, a large value of the liquid to gas ratio is obtained. So the rate of absorption is decreased, and a large number of trays is required for isothermal processes. Heat effects in pack towers. Temperature rise will affect equilibrium curve. For simplicity, it is assumed that the heat is taken up by the liquids and the temperature rise of the gas is negligible. This assumption gives the design of the tower taller than necessary. So this is the graph of the equilibrium curve modified to allow for the heat of solution of the solid. Some examples of systems that separate heat to increase the rate of reaction. Number one is absorption of carbon dioxide in amine solution, and the absorption of carbon dioxide in NaOH solution. And in which systems which heat effects cannot be ignored are systems in which the absorption of ammonia in water and the humidification of air in concentrated hydrosulfuric acid. If the amount of heat liberated is very large, it is necessary to cool the liquid. So in plate columns, heat exchangers connect to the consecutive plate. Cooling coils are attached, or cooling coils can be attached on the plate. So there are two which you can use. You can either use heat exchanger or cooling coils. So in the figure is the glitch truss type bubble tray in the stainless steel for a 1.9 liter absorption. That is an enlarged view of the bubble of the cooling coil. You can see the cooling coil here around the tray. Next, in plate columns, heat transfer coefficient between the gas liquid phase on the tray and the cooling medium depends on the velocity of the gas. It is usually on the range of 500 to 2000 watts per square meter. So it's not usually a problem in determining the heat transfer coefficient. In pack columns, it is more difficult to arrange for cooling. Sometimes it is necessary for the liquid to be removed at intervals down the column to cool the liquid externally. Some approaches to evaluate heat effects are to employ classical isothermal design method, employ classical adiabatic method, and employ semi-shortcut methods derived from rigorous calculations, and to employ rigorous design procedures. You can find these procedures in pairs, so I will not delve more into these topics. But this employing classical isothermal design method assumes that the temperature of the tower is equal to the inlet liquid temperature of the water. And it is most useful if the feed of the gas is sufficiently dilute. It usually tends to underestimate the required depth of the packing by a factor of 1.5 to 2. And safety factors must be added to the design since it usually underestimates. Because there is an equation which will be discussed later.